Hi, this is Professor Jamie Chen at California State University, Long Beach. In this video lesson, we're going to look at logarithmic functions as inverses to exponential functions. We're going to study the log functions and exponential functions as a pair because they are inverses of each other. I'm going to assume that you have prior knowledge on exponential functions, and I'm going to introduce the log functions as an inverse function of the exponential functions. The reason why we study log functions or use log function is because we want to solve problems of the following sort, where x is the unknown, and y is given, and the base a is also given. For example, if I want to solve the problem 2 to the x equals 8, you can answer this relatively easily because I know 2 to the 3 is equal to a. That means x has to be 3. Instead, if I'm trying to solve the problem of 2 to the x equals 10 for x, the problem is not so easy, and this example helps to motivate the study of logarithm functions as a way to solve variable power x in exponential function. Along the way, we're going to need to discuss inverse functions, one-to-one functions, and function compositions. I'm going to start by letting f of x be a to the x. I'm also going to say that this is equal to some known value y, like in the case of 2 to the x equals 8. Y value here is 8. In general, we can see that f takes the input x to produce some output y. We have the situation where the input is unknown, but the output is known. In order to find x, which is the input of the function f, what I need to do is create a function g. I can take the y value as the input to produce the unknown x value as the output. Because in this case, the input is known, all I need to do is plug in y into the function g, and whatever comes out is the desired x that I'm looking for. It turns out that inverse function of f has exactly this property. In other words, all I need to do is let my function g be the inverse of f. Let me give you an example to illustrate what inverse functions relations are. If I have a function f that takes its input values 1, 2, 3, 4 to the output values of 5, 6, 7, 8 accordingly, then what does f inverse do? Notice that in this original function relation here, the output of the function f becomes the input of the function g, which is the inverse. So that means these values, the 5, 6, 7, 8, will become the input for the function f inverse. I'm going to label my inputs the y value from the function f and the x value as the output. Now for f inverse, it will be denoted by the x. So that means I know that 5, 6, 7, 8 would now go to 1, 2, 3, and 4 accordingly. The natural question to ask is whether or not every function has inverse. Let's consider the following example. Let's just say that this function f takes the input of 0 to 0, takes the input value of 1 to 1, takes the input value of negative 1 to 1, and the input value 2 to 4, and the input value of 2 goes to 4 as well. And what this means is that the f of 0, this is 0, is equal to 0, and that is this is 0. F of 1 is 1, and that's this 1 goes to the 1 on the right. F of negative 1 is equal to positive 1, and f of 2 is equal to 4, and f of negative 2 is equal to 4. The inverse function of f needs to take on the values as input from the outputs of f. Look at the list of outputs from the function f. We notice that there are 3 distinct output values, 0, 1, and 4. And that means that in my table, those values 0, 1, and 4 become my inputs for the f inverse. The question now is, where does 0 go, and where does 1 go, and where does 4 go to? In other words, what is f inverse of 0 equal to, and f inverse of 1, f inverse 4? For f inverse of 0, it's very obvious that it has to be equal to 0, because this is 0 going backwards comes from this 0 in the input for f, so there is no question that f inverse of 0 has to be 0. Look at the f inverse of 1, and that's these two 1 values here. It could come from positive 1, or it could come from the negative 1. So there is an ambiguity of which one, which input values 1 or negative 1 should we take. There is no definitive answer to what the f inverse of 1 could be. Similarly, if we look at the output of 4, it could come from the input of 2 or the input of negative 2 from f. So when I take the inverse of 4, it's not obvious which one we're talking about. It could be 2 or negative 2. The fact that there is an ambiguity in choosing which one should be the output for the inverse function tells us that this function f does not have an inverse, because there is no definitive rule to help us assign these values. Each function is not a one-to-one function, because a very famous non-one-to-one function is the parabola of y equals x squared. In fact, that is the function that I use to create these input and output values in the function f. Why is this function not one-to-one? So there is actually a way to test for one-to-oneness by looking at the picture or the graph of the function. For a function to be one-to-one, it needs to pass the horizontal line test, which means that every time if I were to draw a horizontal line, it cannot intersect the graph more than once. In this case, it actually intersected the graph twice, and that is why we had that ambiguity when we have to choose the output for the function inverse. For example, if I were to draw this line, and this is f4, and that's the value here, it can come from either -2 or +2. So you're traversing backwards, the x value here could be 2, or the x value here could be -2. So I don't know which one to choose, the output for my inverse, 4, and that is why it fails to be a one-to-one function. So when a function is not one-to-one, we don't have an inverse for that. In conclusion, we say that the function is one-to-one if it passes the horizontal line test for its graph. Going back to our exponential function example, because remember we let f of x be a to the x in our original setup, we know that the function has the graph looking like this. Based on what we've just learned, this function would have a inverse because it passes the horizontal line test. The question is, what does its inverse look like? It may be easier if we look at a specific example. So let's assume that f of x is 2 to the x. We can quickly calculate the function values based on a set of input values given here. Now the question is, what does f inverse look like? And remember, the input for f inverse comes from the output for the function f. So we're going to take these output values from f and then put them right here for the inputs of f inverse. To find their corresponding outputs for the f inverse, all I need to do is trace backwards to figure out where they come from. For 1/4, it comes from -2. 1/2, we get -1, and for 1 I get 0, for 2 I get 1, and for 4 I get 2. Now going back and plot those points on the same grid, we have the point 1, 0, point 2, 1, 4, 2, 1/2, -1, and finally 1/4, -2. Now let's connect all those dots, get this green curve. What did you notice? If I were to put this line y equals x in the graph as well, you will notice that the function f and its inverse, f inverse, looks exactly like the mirror images of each other along this line y equals x. This makes sense because, for example, if you look at this pair of points on f and f inverse, which are exactly the mirror images reflecting around y equals x line, black dot has the coordinate 2, 4, while the green dot has the coordinates 4, 2. Your x and y values are completely swapped. Another thing we also notice that is the domain of the function f becomes the range for the function f inverse, and the range for the function f becomes the domain of the function f inverse. For example, if you look at this picture, the domain for the function f is a set of all real numbers on the x-axis, and the range for the function f is a set of all real numbers that is greater than 0. But on the other hand, the domain for the function f inverse is a set of all real numbers that is greater than 0. That is exactly the same as the range for the function f. The range for the function f inverse is a set of all real numbers. Notice that that's exactly the same as the domain for the function f. This graph also motivates us on how to find the inverse function when given a function to start with. All we need to do is swap the x and the y variables and solve for y. For example, if I want to find f inverse for the function f of x equals 3x minus 2, first notice that this equation is y equals 3x minus 2. So to do this, I'm going to swap x and y, so make y an x and make x and y, to turn it into a x equals 3y minus 2 equation. And from that point, I'm going to solve for y. I get 3y is equal to x plus 2, and just divide it by 3 both sides to obtain the final equation of y equals x plus 2 over 3. And that is the inverse for the function f. How do I know if that I have actually obtained the correct inverse? Fortunately, the cancellation property is here for the rescue. The rule goes like the following. If you have a set of points in a domain for the function f and call that point x. Under the mapping of f, it takes you to a point that is called the f of x, which is also the y value, or the output for the function f. You now further take f inverse these set of outputs, which by the definition of f inverse, it should take you back to the original x that you started with. In terms of function composition, if we start with an element in the domain of f, and I apply f to it, it should give me this point y. And now if I apply f inverse to this new point y, it should get back to the original x. The successive evaluation of the function is called the function composition, and I can actually write that as f inverse circle f applied to the input x. And this has to be true for every single point in the domain for the function f. On the other hand, if I started with the set of points that is in the domain for f inverse, and f inverse takes x to the point f inverse of x, points you get this way is going to be in the range for f inverse. And we know that from before that the range of f inverse is exactly the same as the domain for f. So I can now apply the function f to these sets of points to obtain this new point that lives in the range for f. But we also know that from before that the domain of f inverse is exactly the same as range of f, which means that this point should be exactly the same as the original x that you started with. This x is also the result of applying the function f to the f inverse. This gives us another cancellation property, which in terms of function composition, I can write this as f circle f inverse of x is equal to x. And this has to be true for all x in the domain of f inverse. So when we talk about function cancellation properties, we're looking at this one and this one. We can now use the function cancellation properties to go back and verify whether or not the inverse I found before was actually correct. First, we need to check that f circle f inverse of x gives us x. What this means is that we should treat f inverse of x as the new input for the function f, because we think of it as this f evaluated at f inverse of x. So this f inverse of x is the new input for the function f. So if you go back to the function f and look for where x occurs, we're going to replace that x by this new input, which is the f inverse. So in that case, we get 3 times this entire expression of x plus 2 over 3. And then I have the minus 2 on the function f. This gives us x plus 2 and then minus 2, which is x. On the other hand, to check f inverse circle f of x is equal to x, I'm going to replace input for f inverse with the entire expression in f. I go back to my f inverse and locate the position of my input x. I'm going to replace that by this entire expression of 3x minus 2 into it. So I would get 3x minus 2 as my new input for f inverse. And I still have the plus 2 and over 3 for the rest of f inverse. If I do this calculation, the 2's cancel, I get 3x over 3, cancels to 3, I simply get x. Those two computations basically show that f inverse that you found earlier is indeed the correct inverse. Remember, when you check for function inverse, you have to verify both cancellation properties. Now that we've discussed enough about the backgrounds of function inverses, including whether or not the function has an inverse, or how you verify a function inverse is indeed the correct function inverse, we can finally get down to the business to talk about the main point of this lesson. That is, if I think of f of x as the exponential function of base a, its inverse function is exactly the logarithmic function of base a x. That is, we really think of g as the f inverse of x. Which means the exponential function and the logarithmic function satisfy the following relationship. We start with ax equals y. We know that the inputs and the outputs of the inverse function are switched from the original function. So I can think of it as now using the y as the new input for the log function, and that should produce the x as the output. It needs to be true for the same base a. For example, if I wanted to figure out what log base 2 10, what I'm really answering is the question of 2 raised to what power gives me 10. Remember, this is exactly how we started the discussion about the log functions, is because we wanted to answer the question like this. Okay, so instead of answering that question, we simply answer this new question: what is the log base 2 10? It can actually be done on your calculator. If you trust my calculator skill, this turns out to be about 3.3219. Now, if you're wondering how you can actually input that into your calculator, because most of the calculators is assuming you have a common log, which is a base 10 log. To calculate something that is a different base than the base 10, we do the following trick. To calculate log base 2 10, you type in your calculator log 10 divided by log 2. The general rule is that if you have a log of base a x, do this in your calculator, you just do the general common log of x divided by the same common log. Go ahead and try for yourself to calculate log base 2 8. The answer should be 3. I want you to carve this relationship in your mind. When I ask you about the relationship between log and exponential function, this is the first thing that should come to your mind. In other words, from now on, you should think of a logarithm functions as a trick or a technique to try to bring down the power x from the exponential function. So if you start with an exponential function where your variable appears in the power position, then you would take log both sides to your function to bring that x down in order to solve. For example, if I want to solve 1 plus 3 to the x equals 6, what I do first is to isolate the exponential function by subtracting 1 both sides. Get 3 to the x is equal to 5. Then I apply the inverse operation to the exponential function of base 3, and that is going to be the log of base 3. I have log base 3, 3 to the x is equal to log base 3, 5. This is just a number you can use calculator for, because that's just log 5 divided by log 3. On the left hand side here, because log base 3 and 3 to the x are exactly the inverses of each other, so I simply just get x due to the cancellation property. So I simply get x is equal to the log base 3 5. Next, let's try to get ourselves familiar with some properties of log functions. We've established that a log function is the inverse of the exponential function a to the x. I should be able to display the log function as the mirror image of the exponential function a to the x. The first thing we notice is that this log function goes through the point 1, 0, and that is true for every single log function, which means that log base a evaluated at 1 should be equal to 0 for any base a. This is true because a raised to the 0 power is always equal to 1 for any a. Property number 2 is that log base a with the input a is always equal to 1, and this is true because a raised to the first power is always equal to itself. Property number 3 is that log base a to the x is equal to x, and this is because this a raised to this x is equal to this ax. That certainly is true for any a and any x. Property number 4 says that a raised to the power log base ax is equal to x. This is a direct consequence of the cancellation property because the a to the x is our f and log is our g, which we know is the f inverse. So if you actually do the composition of f with f inverse, you simply get back to the input x. We use all 4 of these properties quite often. In particular, property number 4 helps us to solve problem that involves log. For example, if I want to solve for x in the equation log base 5x equals 2, according to property number 4, to get x by itself, I need to undo the process of log, which means I have to apply the exponential function to it. So the inverse of the log base 5 is exactly the exponential function with base 5. That means I'm going to apply the exponential function to base 5, both sides. This gives me 5 raised to the power log base 5x is equal to 5 squared. On the left, I simply just get x based on property number 4. On the right, I get 25. A is equal to 10, which means that when the base is 10, we get what's called the common log. But when a is equal to e, remember that e is a number between 2 and 3, we get the natural log. And we're going to denote that by ln x. In other words, I always think of natural log as just general log, but with base e. Similarly, we have the relationship between exponential and log functions as following. We say e to the x is equal to y if and only if natural log of y is equal to x. You can kind of see that by applying natural log to this first equation, both sides. we simply just get x on the left, and then we get natural log of y on the right, and that is exactly the relationship there. I have also the same set of properties as before. Now let's do a few examples involving natural log. Here we're going to solve natural log of x plus 1 equals 2. To get x come out on its own, I need to undo the natural log process, which means I have to apply the natural exponential function both sides. So to do that, I get e raised to the natural log of x plus 1 is equal to e squared. Based on property number 4, I'm just going to get x plus 1 to come out on its own because the natural exponential function and the natural log cancels out due to the cancellation property, and I have x plus 1 is equal to e squared. To get x by itself, I simply subtract 1 both sides to get e squared minus 1. Calculated response comes out to be about 6.39. Let's look at another example. I want to solve e to the x plus 1 equals 0.5. To get x to come down from the exponent, I'm going to apply natural log both sides. To get natural log of e to the x plus 1 is equal to the natural log of 0.5. Based on property number 3, left-hand side simply becomes x plus 1, and the right-hand side is just going to be a number that is natural log of 0.5. So to solve this, I would get natural log of 0.5 and then minus 1. Calculated response comes out to be negative 1.69. This next example, I want to find the domain of the function f of x equals natural log of 4 minus x squared. When I do problems like those, I need to think what the graph of natural log function looks like first. When I know it looks like this. And so the domain for a natural log function, or any log function in that matter, is it's going to be all real numbers that is greater than 0, which means that my input here has to be strictly greater than 0. To set up, my domain is going to be the set of x such that my input 4 minus x squared is strictly greater than 0. Look for this further, I need to factor 4 minus x squared into its difference of squares. That's 2 minus x and 2 plus x, whatever order you wanted to write it, and I want it to be greater than 0. Because this is an inequality problem, I need to do test points to figure out which set is the accurate set. Put down my 2 points, negative 2 and 2. I pick test points in each of those 3 intervals to test. For example, I'm going to pick test points negative 3, 0, and 3. So when x is equal to 3, I would get a negative factor times positive factor, which gives an overall of a negative quantity. But I'm looking for values that is greater than 0, which means this is going to be a false interval. When x is equal to 0, I would get a positive factor times a positive factor, which gives an overall of a positive quantity, and that will be a true statement on this interval. For x equals 3, I would get positive times a negative, which gives an overall of a negative quantity. Again, that is a false statement. Which means that my x value has to live in between negative 2 and 2, not including the endpoints at negative 2 and 2. To write this in the interval notation, it would be negative 2 to 2, parentheses both. The last example here, I'm going to graph f of x equals to negative log base 10x. I'm going to state a domain, range, and any asymptote for this function. First, let's realize that if we let g be the simple log function of base 10, then we can obtain f by simply putting a negative sign in front of g. That is to change the y value to its opposite, but that is equivalent to reflecting the graph of g about the x-axis. If I know my original log base 10 function looks like this, I can imagine that in the background, and then just to reflect that about the x-axis, the function values become their opposites. This function value, for example, goes to the opposite side, this function value goes to here, and so on. The negative function values then go up to the positive side. Therefore, we obtain a graph that looks like this. By looking at the graph, it's easily seen that the domain of it is any number between 0 to infinity. The range is all real numbers, which is just from negative infinity to positive infinity. And there is a vertical asymptote on the y-axis, and that's the equation x equals 0.